Now I want to take some time to have a little bit of an aside about cleaning. So as we move through 1412 here, we're going to talk a lot, we're going to gain a lot more chemistry knowledge that's going to allow us to understand a lot more things that happen in our daily lives where chemistry comes into play, and especially with regards to cleaning, which is a really common application of a lot of chemical principles. So cleaning things is really all about finding a solvent that dissolves what you want to dissolve. And so when you are cleaning things, it's all about what is matching the solubility of what you're trying to get to dissolve. So for example, if we think water is our kind of common thing we use to clean, water is very polar and it forms hydrogen bonds. So it's going to tend to dissolve things that are also very polar, and that also especially solutes that can form hydrogen bonds. So something you may want to clean would be, for example, nail polish. So nail polish is kind of polar and does not form any hydrogen bonds, the molecules that make up nail polish. And so this is actually relatively important. Nail polish is not soluble in water, so it does not dissolve in water. So that's useful because nail polish that did dissolve in water would be a waste of money, because if it rains or you washed your hands, it would be gone. So an important part of designing nail polish, or anything that sort of is an exterior adornment, is that it should be resistant to dissolving in water. Say the dye in your clothes. Otherwise, the first time you washed it, your clothes would lose all their color. So we want to be sure that we maintain that sort of non-polar nature of it. So if we want to clean up nail polish, we need to use a solvent that matches that polarity. That's where acetone comes in. Acetone as a molecule is kind of polar and cannot form hydrogen bonds. That is why acetone is nail polish remover. It matches the polarity of the molecules in the nail polish, so you can remove nail polish. What is happening is you're literally dissolving the molecules. That's why after you wipe it, the acetone takes on the color of the nail polish. You have formed a homogeneous mixture where the nail polish remover, the acetone, has dissolved the dyes and all the molecules that are in the nail polish. And so you kind of see it here on the cotton swab here, that the red or the maroon of this nail polish is in there. It's dissolved. It has, that solution has soaked into the cotton swab. And so that is what you're doing when you're cleaning things. It's all about matching that polarity and cleaning it up. Because then it dissolves and it's really easy to wipe away a solution. Especially, you'll notice we use liquids. You dissolve it into a liquid. It's really easy to wipe up a liquid. When we're cleaning up things like grease and oil are generally very large, very non-polar molecules. And so when we think about, say, chemicals that do cleaning, like Easy Off, this is oven cleaner. This oven cleaner, how it functions is it reacts with those grease molecules that are, say, caked on or like cooked into grease. Those are just really big non-polar molecules. And what it does is it reacts with those molecules and it adds oxygen. So this is a similar reaction to combustion. It's an oxidation process, a reduction oxidation process, where you're adding in oxygen. And so what happens is you take these big hydrocarbon molecules, all of a sudden you decorate them with oxygen. That means they're more polar, which means they are more soluble in water. Okay, so they're more soluble in water. All of a sudden you can wipe them off. If you look into things that are like, less harsh chemical methods for oven cleaner, Easy Off is very harsh chemicals. That is very aggressive. You can look up, you'll find guidance that you can use like vinegar and baking soda. This is still using the exact same mechanism. It is still, you're still putting in chemicals that are going to react with the grease and add oxygen atoms to the grease. You're going to oxidize those grease molecules, add in some oxygen atoms. Those grease molecules become new molecules that are more polar, that have been broken up into smaller polar molecules that are more soluble in water, and then you can wipe them out. You can find a lot of different types of cleaners that are all doing the same thing. It's the same mechanism, and they all have the same end goal. When you're using these sort of chemical cleaners that are reacting with the compounds that you're trying to dissolve, turning them into a new, instead of with nail polish remover, you're matching the polarity. In this case, you're making whatever you're trying to clean match the polarity of your water. Drain cleaner does the same thing. Drain cleaner and oven cleaner have the same active ingredient. It just oxidizes your hair. The hair, the chunks that are in like your drain, it does the same exact thing, makes it more soluble. Now, instead of blocking the water, it dissolves in the water. The final type of very, very important cleaning molecule that we use are called surfactants. And surfactants, that word surfactant comes from surface agent. Surface active agent, I think is how they jammed all those words together. So these are molecules that are involved at surfaces. And so they are molecules that have very polar and very non-polar regions. So sodium lauryl sulfate is one of the most common surfactants that you use. And so if we look at this molecule, sodium, the name sodium is just that sodium cation. So lauryl sulfate is this big thing down here. And so it has these lines, and this is an organic molecule. Each angle on those lines is a carbon atom that has hydrogens attached to it. So this kind of long tail in the molecule is a hydrocarbon tail. It's all very nonpolar. So this part of the molecule is hydrophobic. It's afraid of water. It doesn't want to dissolve. If we look at the other end of the molecule here, you got a sulfur atom bound to a lot of oxygens. So all the oxygens are concentrated in this atom. And so it's very polar. Actually, this is a giant polyatomic anion. This thing is negatively charged. This part of the molecule is very polar and it's hydrophilic. So is sodium lauryl sulfate soluble in water? The lauryl sulfate doesn't matter because this is an ionic compound. This thing contains sodium. So we use the ionic solubility rules. Rule 1 tells us that sodium compounds are always soluble. Sodium lauryl sulfate is extremely soluble in water because there's that sodium hanging out there. So when sodium lauryl sulfate is put into water, both the anion and the cation are going to dissolve in the water. So these lauryl sulfate anions or other similar surfactants are the active ingredient in soap. When they go into water, because the compounds dissolve, because the compound dissolves, you have these surfactants that are dissolved in water. This model here is a bit more old school of a surfactant, but you can see there's still the nonpolar tail that's still hydrocarbon and that very polar head. You'll notice it was very concentrated on that end. And so what ends up happening is these anions, these big anions, they organize in water. The molecules will arrange themselves into what's called a micelle. Okay, so that's a micelle. And what happens is all of these nonpolar tails collect together, right? They're afraid of water, so they collect all together, and there's very little water inside that core of the micelle where there's a bunch of nonpolarness. All of these carbon and hydrogen atoms from all the different molecules are all collected together without much water. And instead, you have this shell of all of the hydrophobic heads of the polar part of each of the molecules. And they form like a shell that interacts with the water, protecting the non-polar hydrophobic tails of the surfactant molecules. So you have this organization of molecules in when they dissolve. They're not forming covalent bonds. Instead, they're arranged as all intermolecular forces, driven again all by the polar differences in polarity. And so what ends up happening is these micelles have this non-polar core. And so what ends up happening, remember again, grease, especially like dirt, is very, very non-polar. It's insoluble in water. So that's why if you have grease or dirt and you just put water on it, nothing happens. It doesn't dissolve. But when you put soap in the water, the soap forms these micelles that have this non-polar middle. And grease is soluble in that non-polar middle. And so literally how you can think about it is these surfactants come down, the non-polar parts of the surfactants interact with the grease, then they form a micelle where the grease is like trapped in the middle. It's like a little pod, and that whole pod floats around in the water and it just washes away. And so that's how we can understand how and why soap works, is all based around matching the polarity. So with acetone, you choose a solvent that matches the polarity of what you want to dissolve. When it comes to oven cleaner, you use some pretty strong chemicals to make the grease polar. So that way it will dissolve in the water you're using. And with soap, you get creative. You have these surfactants. We have this mix. You can intermingle the non-polar and the polar in one molecule, and that enables, you make little basically packages where your non-polar grease can just float away in the water. There we go. Hope you enjoyed this little video. Participation 121, that's what we're looking for questions on. Got 2 more videos. See if we can find some more questions there. See you in the next one.